we feel good about that? Yeah, if you need notes, there's some up here. Y'all let me know what you think. Yeah, that's it. Let's maybe set this up at least. So take a look at number 5 in the 7.2 notes if you haven't done it already. And just take a second and think about how we would set that up. All right, so first we need to, name some things, right? Going to introduce something that's going to represent each of these things. What do you want to use? Okay, X, Y, and Z works for me. H and F and S or whatever you want. Like, it doesn't matter, right? Pick something that's going to represent each of these things. And then just, I can't remember if it was this class or somewhere else. Somebody asked about this yesterday. Like, it doesn't matter what you use to label them, just make sure that you're being consistent, right? So if X is the price of each hamburger, then for each of these 3 equations that we're going to end up setting up, we should be using X for that. So one student buys 5 hamburgers, 5 orders of fries, and one soda for $21. Another does whatever. So we've got 3 pieces of information, right? 3 complete orders. That means 3 equations, basically. What do they look like? Say it again. 5x, 5y, z or 1z equals 21. Okay. What about the next one? Okay, and the last one. X plus y is 4. Good. So that's our system. So again, we see, one of the equations is sort of missing the z term, right? But, again, like, makes it look a little strange, but as we saw yesterday, and at least one of them that we did, I think, if we're, a little bit clever, means that maybe we can get away with doing a little bit less, because the goal in solving a 3x3 is to reduce it down to a smaller, so a 2x2 system. This last equation is already something that only has 2 unknowns. So if I can take the other 2 and get rid of z, then I can use that along with this last equation to set up a 2x2 and solve. So what do you want to do? Subtract a and b, because if you subtract a and b, the z terms are going to cancel, right? So a minus b z minus z is, again, 0. Those drop out. 5x minus x 5y minus 2y, and 21 minus 6. So, again, call that D if you want, but we've got an equation there that's in terms of just x and y. You've got another equation here that's just in terms of x and y. So if I take those aside and, sort of think of that as a 2x2 system, x plus y equals 4 and 4x plus 3y equals 15. Now we're basically doing, what you just did, right? Solving a 2x2. So can I leave it there? We feel okay about, where to go from there? Yeah, everybody good? Okay. Are we okay with the setup? Like how we got from, description of what's going on to the system of equations here? Basically, declare variables, decide what you're going to name everything. You don't have to write that down. I think it's, good to, because then you can sort of tell what you did. But and then again, each sentence, right, each piece of information is kind of one equation. I usually write it so that it is, each sentence kind of represents a thing just to make it easier to read. And then solve that, right? So once we got the thing set up, solving, well, one way to do it, again, not the only way to do it, but one way to do it, the maybe most efficient way to do it, because this last one just has x and y in it. If I can use the other two to get rid of z, then like we're in good shape, right? You don't have to do it that way, but that's one way to go about it. You can also use this last equation, x plus y equals 4, because it's only got two unknowns in it. That would be a place where you can set up a substitution. Solve for x or for y, plug that into the other two, and then you've got, again, two equations and two unknowns, right? That would be, not all that bad. Doing a substitution when there are three kind of gets a little bit messy, which is why we didn't do much of it yesterday. But yeah, good to go. Anybody finish it? Not yet. I don't know what the answer is. It's in Blackboard. Okay, cool. So everybody feels all right about that? Sure about 3 stuff? Okay, cool. I would say for something like a problem on a final, I'm probably more likely to ask you to actually solve a 2x2, and for a 3x3 maybe set up or interpret or something like that, just because you're doing all the same stuff, you're just doing a lot more of it, right? And on a final, you're gonna have enough to do without me making you do a bunch of sort of extra stuff. But that's somebody else's problem for the future. We'll talk more about what the test is going to look like later. Okay, so we're good? Everybody feels all right about stuff? Okay. Then let's talk about matrices. Last set of notes. Nobody get too emotional on me. So I can't get them apart. There you go. Okay. So matrices. That's just the plural of matrix. By the way. Although I do have kind of a fun story. When I was in, I think it was my first year in grad school, I was in a class with a professor who was not a native English speaker. And it was the very beginning of class, and we're just chatting and whatever. And there were probably 8 or 10 of us in there. And he's talking about mattresses, over and over, mattresses, random mattresses, sparse mattresses, large, all this stuff. And we're all like, I don't know. And the thing most people go to in that situation is to just think I'm just an idiot and don't know this thing yet, right? Because I'm just starting grad school, he's a researcher, whatever. I'm just not smart enough to know what he means. And then at some point, like, I don't know, 5 minutes into this thing or something, he goes to the board and like draws a thing and it's a matrix. I'm like, this is a thing we all know really well. And the entire class, like, as one, was like, oh, it's just a really, really nice moment that's always sort of stuck with me. Like, oh, we're not idiots. We just don't understand the word he's using. Okay, anyway, a matrix is just a rectangular array of numbers. So it's sort of a mathematical object. If it doesn't like programming or anything, it's basically the same idea as an array in like data structure stuff. The way that we arrange these is into rows and columns. So rows this way, columns this way. So this matrix is a 2x3 because it's got 2 rows and 3 columns. Pretty much what we're going to do with matrices is we need to just kind of understand like what they are. We're going to do some basic operations for working with a matrix, and then, probably not that big a surprise, we're going to see how this ties into systems of equation stuff. Because like as we saw yesterday with solving a 3x3, once you have kind of the idea down for how substitution and elimination work, like if you can do a 3x3, then you could do a 100x100 system. It would just take all day, right? Like you would just do all the same stuff for a really long time. And that's stupid. And no one is going to do that, right? Look to the very back of this thing I just handed you. There's a 4x4 there, right? Well, to do a 4x4, you would just do all the same stuff we did yesterday. You would just do it like 3 or 4 more times, right? Well, okay, fine. Like I can understand that, but that sounds like it's not going to be very much fun. And you're right, it wouldn't be. But there are places where, really big systems with lots and lots of unknowns in them, like come into play. Like it's not even all that rare a thing for those to come up in different places. So what we're going to look at is how we use this idea, which is a thing that a computer knows how to handle really, really well. Because again, like this is basically one of the like basic data storage types in like programming stuff. So computers know how to handle these really well. Computers also know really well how to do addition and subtraction stuff. And computers are also really good at telling them like do this thing until this happens and then stop. So basically what we do is take the system, turn it into one of these, tell it to do some stuff, and then stop when it gets to a certain point, and that certain point is going to tell us what the answer is, basically, right? So more details on that later, but that's kind of our focus. That's why this stuff is in here and all when it seems at first glance like this is out of nowhere, right? Okay, so anyway, rows horizontally, columns vertically. So this is 2 rows, 3 columns, so it's a 2x3. Now, one of the things that we can do to operate on or work on a matrix is what we call row operations. Basically, it takes a matrix and gives you an equivalent form of the same thing that looks different. Like it kind of preserves the essential matrixness of the thing that you're working with, but turns it into a different form, kind of. The operations that we can use are swapping 2 rows, adding or subtracting 2 rows together, and using that to replace one of them. That's pretty much what we do when we do elimination, right? You take the 2 things, you add them together, you get a new thing. That's what adding or subtracting 2 rows together is essentially doing. Or multiply or divide a row by a constant. Well, again, that's a thing that we've been doing a bunch, right? I need to take equation 1 and multiply everybody by 5 to get stuff to line up. That's that. Swapping 2 rows is just, well, in the system, it doesn't matter if you write them like this or if you write them like that, right? We don't care about the order of the things. So all this stuff is really closely related to what we've been doing. Okay, so let's take a look at just a couple of quick examples of how these row operations work. I'm going to use this matrix as our example. So I'm just going to copy it so that I can see it in both places. This is one of those things that every semester I'm like, I should change that, but then I don't. So this is our matrix that we're working with: 3, 1, -5 in the first row, -1, 2, 0 in the second row. Each of the individual numbers is called an entry. I don't think I said that, or an element sometimes. What we want to do is rewrite this matrix. We want to replace row 1 with the sum of row 2 and row 1. So I want to take the two rows, add them together. You just add, like within each column, you add the corresponding entries together, just like you would with two equations, right? So think of the columns as like the type of thing you want. We're going to add the two rows together, and then that's going to be our new row 1. So I'm going to take this thing. One way that we can write that is something like this. It's not exactly a like standard notation that everybody uses. So sometimes it might be the other way around, like row 2 plus row 1, replaces row 1. Row 1 is replaced by row 2, row 1. But basically, like, do that and put it here. So we're going to take row 2 and row 1 and add them together. So that part is just, again, similar to what we would do with elimination type stuff, right? Add those together. So 3 plus -1 is 2. 1 plus 2 is 3. -5 plus 0 is -5. That is going to go in place of row 1, right? So that's my new row 1. Two, 3, -5. That's it. So here's a matrix. Do this row operation. There you go. That's it. So this is, some equivalent, looks different form of this same matrix. Does that make sense? Are we cool with that? All right. Again, we'll get into like why and what we're going to do with it more in a minute. Now we're just practicing the mechanics. Okay. Do the same thing. Well, not the same thing, but take the same matrix. And do this. Okay, so we want 3 times row 1. Row 1 is 3, 1, -5. So what's 3 times row 1? 9, 3, -15. Minus row 2. Okay, so row 2, I'm just going to copy down. -1, 2, 0. And then the instructions were to subtract 3 row 1 minus row 2. So here's 3 row 1, here's row 2. I'm going to subtract, just down within each column. So 9 minus -1, 3 minus 2, -15 minus 0. This is our new row 2, so it needs to go right there. 10, 1, -15. Okay, we're out of that. Okay, so that's how the arithmetic works within the rows. Again, sort of the things that we're allowed to do, the row operations that we do that aren't going to like change things in a significant way, right? They're going to keep that matrix. They're going to keep something about that matrix the same, right? Let's just say it that way. You can swap rows. So I could, take row 1 and row 2 and swap which one's which. That doesn't matter. That doesn't change anything. You can add and subtract them together. You can multiply or divide by a constant. You just got to do it all the way across the row, and then you can add or subtract. So here we did, we multiplied row 1 by 3. Then we took row 1 and row 2 and subtracted. That again doesn't change anything about the matrix that like matters in a big way, right? Okay, so again, kind of our motivation for doing all this is to be able to solve systems of equations. So if I have a system like this, then if you kind of think about all the stuff that we've been doing lately to solve these, right? Especially like elimination type stuff. As long as I kind of know where everything goes, it's not quite so important that I know that like the first thing is X and the second thing is Y and the third thing is the constant, as long as I know that like everything's in the same place, right? If you think about the like the 3x3 problems that we looked at yesterday, the ones that like look weird where there's weird spacing and stuff because terms are missing. Well, that's kind of why I did that, so that things like line up with like terms, right? So here, again, as long as I know that everything's kind of lined up in the same place, what I really need to know is how many of each one there are, right? So that there are 5 X's here, and that there are 2 Y's here, and 2 X's here, and -1 Y here, and so on, right? So what we can do with that to sort of put that into terms that we can work with, and especially into terms that we can like program a computer to work with, is take the coefficients and just kind of peel the coefficients off once I've got everything lined up in the same way, and represent that with a coefficient matrix or a matrix of coefficients. It's an augmented matrix. It's got this little vertical line. Basically, you take a square matrix and throw a vector on it. You don't care, but think of that vertical line as like representing where the equal sign goes, basically. What we've done here is just line things up so that this column represents the X terms, and this column represents the Y terms, and this column represents like the right-hand side, right? So think of the line as being like the equal sign, and then this is like the right-hand side, which I'm going to start just writing RHS for because I don't want to write all that. And again, sometimes we'll call this thing a coefficient matrix because that's all you do is peel the coefficients off and line things up. So each row represents an equation, and each column represents one of the things in the equation, right? One of the pieces. So there's one for the X's, there's one for the Y's, and there's one for the constant piece. If something's missing, you just fill in a 0 for it. Okay. So how would you write this system in number 3 as a matrix? What would the dimensions be? How many rows does it have? 2 and 3 columns because there are 3 different kinds of things there, right? There's X's, there's Y's, and there's just constant. So it's a 2 by 3. 1, 2, 3, 1, 2, 3. So it's a 2 by 3. And what do the entries look like? Three, -1, 7 is the first row. And the second row would be -2, 0 because there's no Y term, right? So there's 0 Y's in that second equation, and 6. Right? Okay, cool. How would you turn the matrix given there in number 4 back into a system of equations. One x plus 2y equals 7, and no x's plus 1y equals 4. That would be the system of equations represented by this matrix, right? First column is the x term, second column is the y term, third column is the, you got the vertical line separating for like the equal sign. Third column is the right-hand side of the thing. Nothing necessarily says you got to label it with x's and y's, but some kind of thing to stand for each of those is have to be different. Okay, cool. Well, what do you notice about this? If I think about this as a system, it's 2 equations, but are there really 2 unknowns there? No, because we know what y is, right? So if I know what y is, now I can take this and plug back in and find what x is, right? X would have to be what, -1, I guess? X plus 2 times 4. Okay, so having this and having that, I guess I should circle that 0 there. This 0 means that the x term doesn't show up, right? And this 1 here means that there's only 1 of y in that sort of last equation, right, from that bottom row. So what that last row says is that y equals 4. Well, if y equals 4, then really I know how to solve the system then, right? Like we're not quite done because we got to do this stuff in the margin, but we're almost done, right? The hard part has been done. I don't need to do a substitution or elimination or anything because I've already got one of these. I can just sort of plug it back in to find the other. What that means is that if I can take a matrix that's given to us, like if I can take a matrix like this and make it look like this, then we're in good shape, right? The thing that we're kind of looking at here is this sort of lower triangular thing where you have 1s on the diagonal, zeros underneath. That's called row echelon form. And again, if I have that, then we're pretty much done. Like the heavy lifting has been done for solving the system, right? Because that means that whatever that last row is, that's telling me the value of that last thing. Well, if I know that, then I can start working my way back up to find the rest of it. So this works for a 2x2, but it also works for as big a matrix as you want, right? So you can have a matrix that's, gigantic, 100 entries, whatever. But if you've got 1s down that diagonal and 0s underneath, this is all 0s, then what that last row tells you, say this was a 5, what that last row tells you is that this thing is 5. Well, if that thing is 5, then the row above it says, well, I can find the second to last thing. And the one above that, I can find the third to last thing. If I keep doing that forever, I can figure out all the stuff, right? So this row echelon form is, something that we can use for solving a system because, again, we've kind of done, some of the hard work. What about the last one there, 5? If you turn that back into a system of equations, what does it look like? X equals 7. And y equals 2. And z equals -3. Oh. Well, it's 3 equations still, right? But really, that's an answer, right? That's a solution. That's an x, a y, and a z that go together. So I don't have any work left to do. Here I still have a little bit of work to do. Here I'm we're done, right? That's the answer. What's different about this than that? We've still got, this lower triangular, 1s on the diagonal, 0s underneath thing. But what else? There's 0s above it too. Well, the lower triangular ones on the diagonal, zeros underneath thing is called row echelon. The zeros above, that's reduced row echelon. If I'm going to program something to do stuff with this matrix and tell it to, stop somewhere and tell me an answer, this is the thing that we're going to tell it to do, right? Go until you get to reduced row echelon form, and then tell me the answer. And on a TI anyway, other graphic calculators have it built in somewhere. I might have to look to see where. There's a matrix button. And under that matrix button, there's a math option. And under that math option, one of the things it gives you is REF, which is row echelon form. The other thing it gives you right next to that is RREF, which is reduced row echelon form, right? So this is all kind of built in already. So what we want to be able to do is take a system like this and write a matrix. So what would the matrix be that represents this? 2, 1, 5, 3, 2, 7. And if I 2 by 3, throw this in real quick. We'll talk details in a second here. And reduced row echelon form slash some kind of sorcery. This turns into 1, 0, 3, 0, 1, -1. What's the solution to the system then? X equals 3, Y equals -1. Okay. So what we need to figure out is how to do this part, right? But if I can turn this into a coefficient matrix, and I can do the right row operations to get it to look like this, this again, tells me the answer, right? Okay, so we're going to look at like doing the row operations by hand, and then at some point, I don't have a watch on. We'll probably go over into Thursday, but we'll talk about like, okay, now how do you use a calculator or a computer to help you do this? Let's talk about, deciding on how to do these row operations to get that thing where we want it to be, though. So again, this is kind of our target. I want this, at the very least, this lower triangle, ones on the diagonal, zeros underneath. It would be nice if I also had it sort of reduced all the way to have that 0 above. Doing these row operations by hand, though, to reduce this, what you want to do, so our goal is row echelon or reduced row echelon form. So ones on diagonal, zeros underneath. What we're going to do is use row operations. And we're basically going to work on that first. So the first thing I'm going to try to do is get that 0 underneath to basically get the bottom row kind of taken care of. So I've got a 2 here and a 3 here. Again, what we can do is swap rows. We can add rows together or subtract rows from one another, and we can scale, like multiply a row by something. So basically, we're thinking like elimination terms and just looking at this and thinking about trying to get a 0 in that bottom position. So you've got a 2 and a 3 to work with. What could we do so that we can work on eliminating that thing I've got highlighted, that 3 in the bottom position? Think like elimination type stuff, right? Just focusing in on this. If I'm going to add and subtract these together, to get this to go away, first we need them to match, right? We got a 2 here and a 3 here. So what's a common multiple for 2 and 3? 6. Okay, so take both of these up to 6. I'm not going to change row 1 at all. No, that's not true. Sorry. Quick liar. I'm going to take row 1 and multiply by 3, which would be 6, 3, 15. And I'm going to multiply row 2 by 2. 6, 4, 14. Okay, well, that was to get the terms to match in that first column. Now I want this one to go away. So what should we do to get this to go away? Correct. Okay, so now I'm not doing anything to row 1. I'm just bringing it along. But I'm going to take row 2 and I'm going to replace it with row 2 minus row 1. So 6 minus 6, 4 minus 3, and 14 minus 15. Okay. Now at this point, what does the bottom row tell you? That y equals -1, right? Okay, so at this point, we could, sort of jump back out of this thing and say, if I want to think about the matrix as like just another way of doing the bookkeeping for like elimination stuff, right? Like this is just another way to write down what we've been doing anyway, where I don't have to keep up with all the x's and y's and stuff, right? That's fine. You can think about it that way. I can sort of jump out of that and say, okay, y is -1. If y is -1, then this is 6x, 3y equals 15. I can plug back in and find x, right? For the sake of doing it, I'm going to go ahead and keep working on this thing and sort of take it all the way down to reduced row echelon, just so you can kind of see what that looks like. So the next thing that I would try to do is get rid of this, right? Get a 0 in that position. To do that, I'm going to take row 1 and I'm going to replace it with row 1 minus 3 times row 2. Because 3 times row 2 is going to take that 1 up to 3 and then subtract. So 6 minus 0, 3 minus 3, and 15 minus -3. So again, that's row 1, 6, 3, 15, 3 times row 2. So 0, 3, -3, and we're subtracting. All right, so that's where I got 6 and 0 and 18 from. Then the last thing, again, if I'm going all the way to reduced row echelon form, we've got the 0s here and 1 here. I just want this 6 to be 1 instead. So I'm going to divide by 6. Row 1 divided by 6. Not changing row 2 at all. Divide by 6, 1, 0, 3. That again is reduced row echelon form, right? That's all the way down. And again, that tells us that x equals 3 and y equals -1. I know that, some of this looks sort of, I don't know, like it's new, right? It's different. You probably haven't dealt with matrices at all, but I don't know, they usually don't. But like it's kind of a new thing. I get it. We're really just using this as a different way to keep track of the elimination stuff that we're doing, right? So really, it's not any different than that. Although, I know it does look different. And we're a little bit, trying to like force it to work out in kind of a particular way, right? Because we're shooting for that row echelon thing. Next time we will talk about, we'll probably do like one more by hand or something for the sake of doing it. And then we'll talk about like, okay, well, how do I get a computer to do this for me so that I don't have to, manually do all this stuff. But for now, focus on, sort of going from a system to the matrix that represents it or vice versa, and doing, sort of prescribed like row operations.
Can you point them?
Yes, we could have jumped out of this earlier and solved this. Yeah, so you can do sort of a like hybrid thing. I just wanted to take this all the way down to this for the sake of having done it at least once. We'll probably do it one more time, but okay. So that's it. Y'all go and have a good day and stuff. 7.1 to do tonight. 7.2 you should be good to go. 7.3 if I start on it if you want. Yeah, Sean. Say again. Why did I divide by 6? Just to get ones on the diagonal, just to get that reduced row echelon thing. Yeah.